Hello, everyone, and thank you for joining the fourth installment of the Viking Motorsports Design Process Workshops. Today, we'll be discussing the relationships of dynamic systems, how they are comprised, how they're defined, and how typically engineers are uh, kind of confronted with conflict of how do you make sense of this and how do you make it usable. And so this is where engineers kind of bridge that divide in order to uh, kind of bring about new products, new innovations, etc. So a little overview for us. If my thing is okay, overview. This is a simple one today. We'll be discussing the physics backgrounds behind systems and how we manipulate them into systems. And then those manipulations we'll discuss in depth, which we'll call interactions, because most of these manipulations are comprised of a downstream from one system or the upstream of another. And so we'll be discussing that at the very end. And so let's move forward into the first block for the relationships of dynamic systems. And this involves physics. And so what I want to do is to encourage young engineers, everyone here and myself, to follow a first principles conceptualization of the surrounding world and basically its subsequent challenges. It is oftentimes that when an engineer is faced with a massive systems problem or a complicated component that involves a multidisciplined perception, it can then be overwhelming. It causes anxiety or stress. It can also cause someone to feel not confident in their ability to be an engineer. And I want to kind of reduce or minimize those perceptions and stigmas because I think anything is approachable and conceivable given the right tools. So, for more background, basically, the purpose of physics, as ancients would describe it, is that it's essentially the knowledge of nature. That's what it was derived from when it was historically created. And basically, what it seeks to do is quantify our surrounding world. And the last bullet there is, I think, was said by Elon Musk, but it could have been someone before him. But he put it into a great concise manner, which is essentially to say that physics allows us a subset of equations that govern, model, and predict. And that is true in all aspects because we have prediction models for meteorology, seismic events, temperatures. We have models for movement, accelerations of cars, or even accelerations of societies and how they will grow. And so these things that we kind of adhere to ensure that our quantification of the world is sound relies heavily on physics because it is a natural or fundamental knowledge of nature that we use to exploit in engineering practice. Um, and essentially, what all natural scientists and physicists essentially wanted to do is understand how the universe behaves and interacts. And when I say quantify the surrounding world, that includes the universe itself. And into the next kind of discretization or the quantification of domains. And so this is very important. And it kind of helps us to ground or foundate ourselves into what domain and is relevant to our application. And this is physics-based domain. We have classical mechanics, relativistic mechanics. Albert Einstein is a famous relativistic uh, scientist. Classical mechanics, another one, or classical mechanics is based on like Isaac Newton. Quantum mechanics is based off of, say, like R.M. Feynman. He was also a great contributor to quantum field mechanics and also quantum field theory, which is probably the latest and newest field of exploration because it essentially breaks all classical mechanics interpretations and how we quantify the world based on that domain. So it's a really interesting time to be alive in this world because of the advancements into the quantum field theory that then reject the conjectures or theorems posed by classical mechanics and its scientists. Um, and so engineering fits into the classical mechanics because we're involved with the greater, bigger bodies and not necessarily the development of those bodies. However, there are engineering titles that will involve relativistic mechanics, quantum, and quantum field theory that then are then trickled up or manifested into classical mechanics. If you're all familiar with Neil deGrasse Tyson, he once famously said that engineers are essentially the commercialization or industrialization of a product or service. And that means we take all the research that physicists or scientists produce and we put that into a system that consumers will use, we would use, and what the industry uses. And so that's where engineers kind of fill that gap. Now, here are some iconic physicists that I wanted to briefly touch on. The first one is Isaac Newton. He's very, very prominent in terms of the laws of motions that he founded and proved. There is also Albert Einstein, which his theories of relativity and which concerned light, the universe, and how time interplayed with space. We have next is R.M. Feynman, or Feynman, I probably butchered his name, but he's involved with quantum field mechanics, field theory, and quantum mechanics, and he helped to kind of push the levels of microscopic thinking or quantum level thinking of physics. And another famous physicist is Stephen Hawking. He's also world renowned for his exploration into the universe and how physics is defined from the Big Bang theory, very closely related to Neil deGrasse Tyson. And so these are some, very competent people, and obviously their names have rippled throughout time, and therefore we now base a bunch of our now used mechanics on the findings of these people on the backs of their work. And interesting enough, they don't go and sue for credit when their work is used without recognition. And so in terms of engineering, we're mostly concerned with classical or modern physics. And this is because we seek to deliver a solution to a problem and within an envelope of problems. Ones that we know beforehand or during or after the fact when, say, a product is at the end of its lifetime or during retirement. And essentially, we're here to optimize the surrounding world as best we can. And that involves commercialization or industrialization. And to go forward, similar to emerging ancient civilizations like the Mayans, the Romans, the Mesopotamians, they all encouraged growth and resilience through the practice of engineering. And so you can kind of understand why it takes multiple disciplines and cultures and the interactions between those disciplines and cultures to push forward a nation into a power. And so I wanted to kind of shed some light on the history of engineering and some ancient engineering marvels which you may be familiar with. The first here is a Shin Bashira, and essentially what that is a seismic resistant temple that was used to worship. It relied on the art of joinery or ancient woodworking techniques that did not use our typical modern conventions of joining or fastening multiple pieces. Instead, loosely constructed wood beams paired with a giant damper or beam throughout the middle of the structure, which you can kind of see here with this tall beam here. This was the extension or the protrusion of it from the main beam that is found within the center of the entire structure. And that beam was there as a damper for seismic activity. So if there was a seismic activity, it wouldn't load the entire structure. It would instead be concentrating that seismic load onto a single beam that would then dampen that seismic motion so the structure wouldn't receive any damage. And this structure has been able to last for over 2,500 years without the conventional methods of joining, which shows a lot into Japanese industrialization and thinking into how they approach problems. And so I think this is a great ancient engineering marvel example. Another example is the water wheel. And this was initially invented by the Romans. And what it sought to do was to harvest water from distant locations and bring it into villages or cities or towns. It was also used to assist in crop irrigation and not only just for plumbing and irrigation for civilizations. It also helped with the grinding of grains and mills, and again used to divert water. And of course, this couldn't have just worked without, a wheel and place it on the side of a building and allow water to flow over it. There had to be some supporting infrastructure that had to accompany this, and this would be known as either aqueducts or dams, um, which enabled these innovations to occur. And as a systems, it generally benefited as a mutual benefit throughout society and for the articulation into Roman technology. The next example I'd like to bring up is actually the first known steam engine. This was done again in Rome, and this was known as an aeoli pile or aeoli pile. And what that was it converted an atmospheric or pneumatic pressure, which was steam, and converted that into motion. And by doing this, or which was used as a steam turbine, and by doing this, it helped to kind of bring the notion of how do we convert to energy from different processes. And this was the first example. Essentially, what the aeoli pile was a simple, vaneless radial steam turbine, which spun during the heating process of water and ejection of steam from a tip jet. And so water heat up here, either use of capillary action will force the water into a cooler region, which would be in this turbine. And then by the turbine ejecting these steam profiles or stream tubes, as a aerodynamicist would call, a momentum of it. And so modern engineering marvels that someone is, or most of you would be familiar with, is the uh, here on the top left is the sustainable city. This was founded in Dubai, and this is another picture of the Burj Al Arab. This is also in Dubai, and these two are really interesting because this sustainable city is 100% powered by renewable sources of energy. It's a net zero city where water is recycled. Uh, there's even solar panels. There's solar panels that cover this entire city complex. It's on every building, over every parking lot. Uh, it's it's pretty insane in terms of investment and the micro scale management of a city. That shows how much we can implement that into major cities. Minus the retrofitting that would have to occur. But the idea is that if a city was conceived uh, sustainable from the beginning of its design idea and implemented at the end result, it would therefore be a better implementation of sustainability instead of it being an afterthought or having it to be retrofitted to an already existing city. I believe this will be the future moving forward for city development if there are new cities to be uh, kind of integrated into infrastructure. Uh, Here is the Burj Al Arab. It's a very impressive engineering marvel because of the fact that there's a lot that goes into the construction of a building of this shape. Um, I remember watching a documentary and it stated that from this platform to the top, there had to be some sort of innovation along the way or during the process of constructing it that had to be overcome in order for this building to have a lifetime of X amount of years. The real amazing part, I think, is either occurs at the base and it occurs at the top. And at the base, there are basically concrete blocks that dissipate the energy from waves or from ripples, and then dissipates them onto those same ripples from which they came, to then therefore negate the incoming energy from those waves or fluid particle motion, basically canceling each other out to no longer have an effect on erosion, or to minimize erosion for that fact of the matter. Another innovation occurred here at the top, and what that was to create a cantilevered lookout point for a dining area or restaurant, and to hold that, to make it look like it was quote unquote floating. The engineers had to hide a span of beams that kind of fanned out, and it would have the structure over it, but those beams would then be hidden underneath the underlying part so that it looked like the lookout of a sail or of a ship would then be covered, and you'd only have the experience of dining while floating. And that was the notion there. Again, the Burj Al Arab was conceived by I think the prime minister of, or the president of United Arab Emirates. And he wanted this to be a symbol for the country in terms of engineering and prowess. The next example to the right, this is a Tuatara engine, and this was I think a twin turbocharged V10. And this engine is incredible, and the engineering and the process and components behind it, because it now just broke the land speed record, which I believe is now set at 316 miles per hour, which smashed the Koenigsegg record, and it smashed the Venom record by nearly 70 miles per hour. And this is really incredible because it's very difficult when you're trying to beat the land record, because drag increases at the squared rate of velocity. And so this has to overcome that, the engine power plants has to, and a bunch of other techniques to kind of achieve that speed, required a lot of engineering behind it to accomplish that feat. The next example is an assembly line, and basically to say automation of processes. Automation has pushed the world into a different direction and relied and created new revenue streams, but also creating new fields of for the industry. And this is very interesting because although it does replace X amount of jobs, it does create an X amount of jobs. However, those two that are destroyed or created aren't equal. However, I would say that moving forward into an autonomous kind of world is scary, but in the form of an industrial need or practice, I find that automation is very suitable. And with all of this said, I wanted to kind of encompass that innovation doesn't have to end. And innovation can come from any source of inspiration, essentially. And all of these systems are founded on a basic principle that a system relies on this process for that product to be a result of it. Now, when you think about where the origins and the end results are, there are very, it's a very complex system. You have, say, raw materials that then are processed, that are then goes through another second post-processing solution, and another second post-processing process. Which will then lead to a product, or then be fabricated once more into a product. And so when innovation does strike, typically you want to disrupt markets. If you do innovate, or if you quote unquote innovate into a market that already exists, it typically isn't perceived as such, because you still require a front end effect for you to have a everlasting change in the outcome of that effect. However, if you were to change what's needed in that process of getting to a component or a material, that is where you disrupt industries. And one example of that is Moji Metal. Essentially, they are a multidisciplinary startup company that relied on a process known as nano-laminated structures. And these nano-laminated structures involved disciplines of teams from physics, chemistry, electrical engineering, and mechanical engineering, and material engineering, and all their research. And essentially what it is that materials are built up similar to additive manufacturing or 3D printing. However, it's based on a nanoscale instead of a milliscale. And what that in turn does allows the modular metal team to put forth each layer of metal that's successively built on top of the predecessing layer. And you can then achieve forms like this without having to use any post-processing technique such as milling, lathing, or maybe even a forging process that I have to go about to kind of create the structure. Instead, you just build it out of the tub in this form. So you're able to take a donor material, use an electrolysis process to create current and time-based controlled current to create this layer structure into a bigger component. And this is actually revolutionizing the industries of oil, gas, aeronautics, civil, such as bridges, marine, aerospace. It literally impacts every industry, and this is what I would define as an innovation. So modular metal is currently in some hot water, but I hope they can come out successful and actually bring forth their products into commercialization, because it'd be really interesting what the capabilities of engineers would be if, say, a material could last 15 years instead of 5, or a component lasted 15 more years than a traditional, like 10 years. So this would be really interesting to see in the future. And now that I've briefly touched on these systems that are encountered, we're going to move forward into systems. So the objective here is to develop an approach that quantifies an engineering project at varying scopes. And so what that means is to kind of perceive the scales and I guess what's involved at that scale to make sure you have an end result throughout the engineering project. And it's very difficult to grab because initially this is what we think of a systems project. There is a bunch of loops, there's a bunch of components within each loop. Not each one may be the same. Some can change by a degree or 3, or the amount of pressure it can stand by 1 or 2, because again, engineering is the art of compromises, and another compromise is cost. And to include that, we have to radically ensure that while we can make a component that has a bunch of dangerous operations, that it must be safe, reliable, and repeatable. And so this is what, it's very, very overwhelming at this point. This is a piping and instrumentation diagram. And simply it just is an example of a schematic that illustrates processes, the system of interest or boundaries. So for example, we have fluid here, which is a region gas, which is, find the arrow, goes through this process. We have hot oil being ingested here, goes throughout this process. And we have the partial stroke test and the output of the regen gas, which is then throughout this silencer, and I believe this is a scrubbing tower. And so what I want to do then now is, yes, this is the initial perspective. We can also break this down into something much, much simpler. So this is an example of an electrical circuit that controls through some sort of controller the motor, which then has an output torque on the shaft, which that shaft then feeds into a gear set, and that gear set has a certain ratio to achieve a specific torque, specific speed at whatever time or whatever meshing they require. And this work of mechanical teeth and collapsing or meshing is then output to an output shaft, which would then be instituted by the load for which it's trying to feed into. And so what I want you all to understand is that it doesn't have to be overly complicated. It can be very simple as long as you understand the assumptions that you're making, the tools that you're going to use to assess this, the relevant equations, etc. So this system here in front of us is a drivetrain, essentially. Of course, there's some other things that are missing for our particular drivetrain, but this is a drivetrain, right? So again, there's an input current with a electric voltage potential that is applied or that exists. And that voltage potential is then transferred here through the current, or not transferred to the current, but the load is then acted on by the motor through the voltage source or potential that exists. And so we have a DC motor that takes an electrical signal that is then converted uh, by the motor from electrical work into mechanical work. And then that mechanical work is then translated through a shaft, which we then call shaft work. And then that shaft is now acting on a gear, which would be here. And that gear in a gearbox is then mechanical work or friction between these teeth, and as well as the displacement of that work onto each other to spin or create a rotational energy that is conserved into this work of output, of course, with some losses, that is then directed to the output or the load, which was then required for that signal to determine how much of current is necessary to spin the motor for the required load. It's expected. And so some fundamentals of system engineering as prescribed by NASA. It is the engineering process or the art of compromises and decisions that requires a methodical, multidisciplinary approach for the design, realization, technical management, operations, and retirement of a system. A system, quote unquote, is the combination of elements that function together to produce the capability required to meet a need. Does it sound familiar? Well, it should be, because that is the premise of a design process in general. Now it's just being modulated into system engineering. And so we also have to include the fact of team dependencies and integration. And this can become very overwhelming, but do not lose confidence because you need to trust the intuition that you have developed throughout school to guide you in your decision-making processes. And to understand that, there are some tools or say governing equations, laws, constraints, and procedures, or software, and again, that self-intuition that helps engineers to make these decisions. Now, I just want to remind you, there are certain laws that have to be conserved throughout any process that involves energy. For example, there's the conservation of energy, there's conservation of momentum, conservation of conservation of pressure. That's the only two I can think of. And there's also an equilibrium that you need to understand for any system. Say what that means is like a static system or a thing or an object or a component or a thing that has nothing acted on, but its static structure is what is in equilibrium. And if there was an external force acting on it, there could be something that changes, or an external input that acts upon it that again changes something. Again, a lot of these laws overlap, and this is where the idea of superposition is really insightful for engineers, because just know that if you have one load acting on a certain component and you want to add another, you simply add another load. But if it relates to mechanical, add another load. If it relates to electrical, I can't specifically speak on the process of superposition. And fluid loads are also, again, superpositioned because of the fact that they can just be overlapped. And so one thing we also need to remember is the value of our coordinate systems. Sometimes we have to convert between Cartesian, polar, or cylindrical, or spherical, and their respective translations. Sometimes we have a linear motion that has then to be converted into a rotational motion. It is then translated into compressive motion, which is then translated or converted into an electrochemical process, for example. So an example of what these governing laws can be is something known as dimensional homogeneity, or I like to call it a sanity check. And what that involves is using a method known as Buckingham Pi. And what that is to determine dimensionless groups of variables needed to define a problem, or to assist with the initial tracing of a variable from a known answer. And what this helps us to do is basically compare our units as well, as to ensure that if our end result that we need is, say, uh, a torque, which is a Newton meter, right? If we were to go from any specific beginning equation, if we had X amount of variables that we were given, if our manipulation of these variables do not equate to an end result of Newton meters, therefore our method of solving this problem isn't applicable, and we should then go back to the drawing board. A lot of times units get lost, and I've done this multiple times, as units as well as scale have been lost. It's also very important to understand what changes when you translate these scopes and scales into your processing of calculations. Another intuition you should have is understanding your frame of reference and the reference points that coincide. That could either be a ground or a ground plane, it could be a ground beam, it could be the ground from simple beam, a simple supporting structure of a beam. And also to understand that gradients exist. Everything would move from a higher concentration to a lower concentration, and that is the basis for the exchange of internal energy for a lot of different processes that are familiar to chemists, engineers, and biologists. And so for that basis, we should also think about how energy or mass would transfer based on those gradients. Some software that everyone's aware of is obviously Excel. A lot of people like to use MATLAB. And other computational software such as Abacus, Star CCM, ANSYS, like CDP Adapco. There's also Siemens, and SolidWorks has their own kind of software. And it's really great for shortening time or turnaround time for hand calculations, or to compare your hand calculations. And it helps with the initial direction of a project, or to say, hey, am I on track or not? And also provides greater flexibility in terms of design, because then we can, if we know that if it works for a simple model and we then make that model much more complex, we are not kind of inhibited by the software, but the user is what inhibits the software. But that flexibility that I was talking about allows us to make much more organic shapes as AI would, or to understand the transfer of loads within a mechanical material, the transfer of heat or energy between systems, and etc. And again, the tools are not as good as a person who is using them. And a big tool that every engineer should utilize is their self-intuition. It involves using appropriate scope when necessary, and you always want to move from a simple static case or reference point to multiple nodes of mechanics or different types of analyses. And it's as simple as ensuring you draw a free body diagram, you write out your governing equations like F equals ma, or F equals 0 for a static problem. There's no input for static problems. Or T equals 0, or delta T equals 0 at X equals 0. And those are basically saying those are your initial conditions or boundary conditions. And that includes your frame of reference. And so if you say have a transient problem, then you would say have a shift in time that is, or a process or equation that's dependent on time, and that's what a transient problem involves. And then there's also a non-transient or a steady state problem, and that involves something that will operate at this level for infinity. And so what is the quasi-static approximation here? Also to understand that to give yourself reasonable assumptions, and as well as the expectations or what you're cutting out from these assumptions should also be noted and carefully considered throughout your engineering process. Because when you throw in a ripple into your analyses, say if I add time dependency into a problem, then the governing equation must also change. And so you then have to go back to the drawing board and start over again with these different assumptions. One assumptions that you make is, say, in a different mode of heat transfer, there necessarily wouldn't be any change in time. But so if you were to add or superpositioned mode of heat transfer into a problem where you only considered a single mode of heat transfer, you then adding second mode would then add that superposition technique I was talking about without changing the governing equations that led to that principle, because it's not time dependent. And typically, when there's time dependency, or if you want to choose a quasi-static approach, there must be a final state and a initial state, which must be defined, and then which is then compared to and analyzed with. And so it's very important as an engineer to use these tools often and almost to have that procedure in good technicality. And so those relationships we talked about, some questions that you want to start asking yourself is, how do we define a system? You know, what is the main focus of the problem we're solving? And, you know, what's involved with solving said problem? And so some key questions as engineers, as we've just discussed, we must operate on a responsive, reactional, and causational basis. For an engineer to think anything otherwise would lead to insanity. It would lead to the lack of a result or an outcome. And so it's very easy for an engineer to kind of get trapped in this bubble or rabbit hole of non-conclusive solutions. And it's very important to understand that what you're trying to solve is appropriately handled. An example of this would be like fracture mechanics, material science, and engineering. And what this is involved with is determining the source of fracture within a specimen. This job also pays very well for those who are interested. And what it does is determine the source of fracture within the specimen. It relies on crack propagation, the direction, the kind of shapes that are involved with the crack propagation. And again, this is done with electron microscopy, which is SEM or TEM, so scanning or telescoping, or transmission-based, I'm sorry. And it also is important for engineers to think as the problem as an all-encompassing situation. And for that, we must be inclusive thinkers that have to move forward to a single goal. Simply, if there is no goal, there fails to be a purpose. And for that to happen, we define the end goal, which we said in the beginning of this workshop series, to accomplish a solution in terms of what's needed or defines the needed end goal. And so we are trying to find these relationships, right? As I briefly touched on, we have something known as transient and we have something known as steady state. Again, these are time dependencies of a transient equation being used to solve a problem, or do we use a quasi-static or equilibrium approach to solving a problem? And this is mostly inclusive of, say, heat transfer, fluid transfer, anything that's time dependent. Cyclical fatigue loading is also another example. However, it would look like the second-hand side of the left graph, which would be the life cycle of a product or a beam. And so the one on the right should also seem familiar because it illustrates the states and properties of water as a function of pressure, volume, and temperature. And so these kind of relationships are benevolent throughout all practices and disciplines of engineering, and they vary greatly. So if you're in electrical, you're going to be dealing heavily with signals. So the left-hand side may look more familiar. I believe that's like a square wave almost. You can have triangle waves or sine waves. Essentially, everything's a sine wave. And it's important to understand the relationships that are involved. So that's what these graphs were discussing. And so we, as engineers, we have to then rationalize these relationships. And so how we go about doing that is that we must follow a convention to solve a problem. And this can be either through a control surface approach. We can use a control volume approach or an open system approach, or a closed system approach where it dictates that no mass can enter or exit a system but energy can. We can think of it as time, inputs, which is feed forward, and then we have outputs, which is known as feedback. The key is to remain consistent and develop a coherent procedure in order to replicate results. And say, for example, if you're working on a kinematics problem, you always want to set up a free body diagram. That is true also for a statics or dynamics problem as well. From the scope, we need to understand that things operate at the quantum or nanoscale, and then we also have general macro scales that are outside of a component realm or a high level, which is a system realm, and everything is a function of the other. And so, as an example, for tires to behave as advertised, right, the width, the radius, the tread pattern, the sidewall strength, and essentially the rubber compound, which is conceived of the tire, are considered then designed towards or designed from. And these are either your key performance parameters or identifiers, or your performance goals. And then we need to think about the intention, the reaction, considerations, and assumptions. And basically, you want to ask yourself, does it move? Does it rotate? Does it translate? Does it convert? Another thing to ask yourself, is it necessary? Again, these are part of your sanity check. And can we simplify this, right? What are the assumptions that we're making? And so having a way to rationalize these relationships is very important for engineers to define dynamic systems in terms of each other. And this is typically done through a system efficiency or a work or desired output over the input that you're giving a component or system, which is efficiency. Systems can also be related in terms of a block diagram is also a way to kind of understand those function relationships. However, let's kind of go into an example here. If my screen decides to load. So here at VMS, we're going to be looking at typically race car engineering of what involves this dynamic system to exist and how everything coexists so that we can make the safest, most rational decision for designs and every subsystem, for example. So when we look at systems, I'm going to share my screen. All right. So the example that I wanted to illustrate here is that we have a car that has this intention, and that intention is to, awkward. So that intention for this car is obviously to place first, right? You want to be the winner. That's the whole point of a competition, right? So what interacts or what involves you to win, right? That is in terms defined by the tires that we have, right? We have smaller ones in the front, wider ones in the back. Why is that? People would say it's for traction control or to increase the contact patch of the tires. Then we have, say, from the tires, the reason why we start there is because we have, say, a ground. So this is our ground right here. And we know that from the ground, we have an input from the road that gives us friction or typical aggregate mix that we then manipulate throughout each track for a tire compound to give us the best results in terms of handling, gives us that circle of good handling for a car, and or the traction circle, I'm sorry. So anything out of those bounds of this traction circle would then cease our whole system to function as intended. And so with that intention, we then carry that any load from the wheel or within the tire, which is then translated into the suspension linkage, which is here, which I'll move to red. So we have suspension linkage here that kind of operates at a certain point with, say, an upright. And then to make those uprights spin, we need to translate a engine, which would be right here, which would then move through a shaft, say here, into a gear network that then causes these these axles to spin. We're also concerned with how slippery the car is on the track to help us win, because our intention is to win. So we also must consider the air moving over the car that kind of follows this path off the wings, or it goes underneath, which I should probably put in yellow. So it goes through here or through the side pod and out the rear. So again, we have air going over the car. We have air going under the car or around it. And so aerodynamics, or fluid movement, is also very notorious in this system. Another thing we must look at is the safety of the cockpit or the chassis. It must be rigid enough to withstand a certain load or impact. And so we have this frame here, which must encompass the driver and must make sure that they are safe and comfortable for them to win. That is our intention. And to solve that intention or need to win, we must make sure that the driver has the best chance to win. And so now that we have the kind of systems within a systems defined, we can then move forward into the system boundaries. So, right, we could take the whole car and say, we'll just say that the efficiency of winning is equal to the efficiency of the subsystems. So let's say suspension for wheels. So it depends on the efficiency of frame, and it depends on the efficiency of, I guess, power. And so for us to have the highest chances of winning, which would be 1 if we did win, right, we have to ensure that all of these systems kind of cohesively are integrated and they operate as such. And so when we define a system boundary, which will not leave as those efficiencies, right, we have our first boundary here, which would be the tire, which includes the road, because that is the change, or it is the not a closed system, but a control surface system, or a radial system. So this again relies on coordinates such as maybe r and theta, right? We have torsion or torque. We also have friction that is involved. Here we have inertia, and we have a certain mass that's applied here. And so when you develop a system boundary, you basically do a dashed line, and this dashed line tells you what you're going to analyze and what you're not going to analyze. And so to complement that, say if we were to work on the aerodynamics, right? If we're focused on the front wing and say we only want to look at the front wing, we wanted to draw a dashed line around the front wing, like so. And so what we then would be looking at when we have a system boundary defined, right? We have certain views. So we have some top view, and if that wing were to look at from the top, we have an extension here. We have most likely a curved wing profile, such as that. And so here we have the cutoff here from the nose. We say that if there's any force from the vertical direction being exerted, we can't see that because we're in the top view. But if we went into a side view, we can then see the remaining interactions of this component. So we would have, say, an uprising from the nose. We have these kind of catenaries, I believe they're called. And then we kind of have the front profile of the wing to which this part connects to. And so then we can actually see the flow field that is generated if we had it come from the right-hand side. So we could then synthesize, say, a flow field. Right here we have a velocity of whatever this, the vehicle speed is, which is Vs. So now we can find a flow field around this, an implicit one at least. We could also then see what the loads are from downforce. Say if we had a force of download or downforce load here on the front part of the nose, right? We can then give us the sine theta in terms of the direction from which we reference. So if we were to draw a free body diagram from there and say that's our x, that's our y. From here, we can then orient or reorient the vector into being a vertical line. And this is that relationship here, because we're trying to find the resultant of that force, essentially. And for example, for the top, if we want to figure out the, like the drag coefficient, I believe is like CD equals half mv squared times the frontal area, I think. So if we wanted to find the frontal area, right, we would take, say, this dimension, which is x, times whatever height we say is 5. So we know that AF, or the frontal area, is like 5x. And we say that our V equals Vs. And we have the mass, which is known. We could then theoretically figure out our drag coefficient as a function of the width of the front wing. So again, system boundary is very important because it allows you to dissect the problem into a much more relevant or useful scenery for you to figure out the problem you're solving. And that is my quick take on system boundaries. And now let's think about scope. And so the scope is really important for a system because if we're, say, like a subsystem, right, our subsystem for frame is literally the entire body, right? For frame, it's very difficult, but frame doesn't have to worry about, say, the power displacement as much because power displacement is dependent on the power team and whatever high-level decisions that incurred from the power plant design. But one example of scope is, or how to define that scope is, where do we want to analyze a component at its place within a system? And so say if we're concerned with how, I guess, like the differential is compared here. So say we want to get to this point, right? So for us to analyze the drivetrain, which is what we want, or the differential, I'm sorry. So if we care about the differential, right, we care about how the wheel is compared to the ground. So we have our reference that we defined. And so if we want to get to the differential, we start from the ground. And basically you draw like a line as to where, a line with a node system to where you want to get to. So by doing this, what I typically do is I'd say I start from ground, I move up into the center of the wheel where exists a shaft, right? So that shaft, again, translates motion for me, a rotational motion into shaft work. So from that shaft, I would then drive into the differential. So it took us one jump there and another node there. So solving our differential requires a two node interaction. And so then we must then define our system of a differential in terms of two different interactions. And those interactions, again, are from the wheel that we previously described, right? That's contacts the ground. And we then have a CV shaft or half shaft but essentially, and what that does is it connects, let's say, the ground to differential. And so ultimately, what we've then now just figured out is that for us to prescribe our differential in solving for X amount of problems, using Buckingham Pi kind of thinking, right? So we have friction at play, we have certain tire depth or width. So we have width of T, we have the radius of T, we have the yeah, that's actually all we need for a very initial construction of a problem. And we have a half shafts, which uses the shaft work. So, and this is actually the force from the wheels, which we would acquire from the wheel interaction. And the half shaft interaction is simply torque, which is 2 pi n. So, or times the radius, I believe. And so torque gives us, for a certain RPM and a certain tire radius, so RT actually, or wheel or tire radius. And what that gives us is a torque value, which is then converted onto the shaft, which then spins into the differential. And along that length, you have a change in torque value. And so the differential must be able to handle maximum torque that is subjected to from the half shaft from the tire. And so kind of thinking of what defines what helps you to figure out your scope. And so that way you don't kind of get lost in the whole, maze or analysis paralysis that kind of inhibits progression in projects. And so scope is really important, but understanding the nodes and interactions between your system and a reference point is very useful to define that scope so you can better solve your problems. And so I want to go back to the presentation, which is here. And so now that we've kind of made those intentions, reactions, and considerations and assumptions, we then know our boundaries and scope for a system as they're kind of bluntly described. And so I want to then now touch on interactions. And so interactions, what they typically involve are the must conceive and think in terms of work. So work has a magnitude and direction similar to vectors that will dictate the overall interactions and work between systems. The fundamental unit for any type of work, whether that be electrical, shaft, spring, fluid work, electrochemical processes, they do have mass that's involved. Yes, they do have a certain time variance involved, but essentially the standalone unit of joule is not dependent on anything but energy itself. And so when you can think of work, which is a transfer of energy or of work between systems, it typically just requires a conversion process for us to get there. And it's very difficult to think of in terms of energy, frequency, and resonance until you kind of delve deep into the base or the origins of physics and how basically the world functions as a whole. And then the natural and artificial world then becomes less intimidating. And so, again, you may require knowledge of various industries and components to start, and ensure that your case scenarios start simple before you move into a more complicated process or analysis process. Work transfer examples are, yes. So basically for work to occur, there has to be some sort of input. And so if F equals 0, we are doing a static analysis, but because we're not doing static analysis, we're doing work transfer. So that requires a mass or an acceleration of a certain body. And the bodies could be, a piston, spring, it could be an electron, it could be a beam, and it could also be fluid particles as well, an aggregate of fluid particles. And so moving boundaries typically involves a force and a displacement, which then acts upon a system within that system boundary. And such as acceleration of bodies, which is like Newton's law of motions. And for example, of electrical work, there has to be a voltage potential that exists, and there must be some sort of load attached for current to flow. Shaft or spring work involves components for a shaft that is typically rotating, and spring work typically involves components that store or exert energy during your process or for analysis of beams, for example. And another type of work is fluid. And this could be like an analysis of air moving through a battery. It could be, what does the air moving around the car look like? And so you have these velocity maps that come from fluid transfer. You also have energy maps and turbulence maps and eddy maps as well, which is basically a velocity map. But some example of components that foundate on work transfer are things such as like for moving boundaries are like pistons, dampers, belts, chains, and gears. For electrical components, this is very brief, but it could be like MOSFETs, resistors, transistors. Photovoltaics is another example. Some shaft or spring work, again, obviously are shafts and springs, but this can also be entailed into like push rods, which translate displacement of a vertical or axial load, or as opposed to say a radial load. And then the fluid work, which could involve hydraulics, pneumatics, typical things such as one-way valves, orifices, rudders and blades. This could also translate into diffusers or the vanes that are made from them. And this could also be like, say, a steam engine or generator that involves pneumatics. And so these interactions, as much as they're intimidating, we must find a good way to document these findings or this research that we're doing, because we don't want all of our effort to be for nothing or lost within the next year or two, because then it would cease to be useful and could also hurt the successive team if they want to build on the knowledge that was founded from the previous team. And so good engineering practice involves the designation and consideration throughout the entire process. And so at Viking Motorsports, it adheres to the general consensus of industrial and engineering practices. The team's standard is to keep record of progress, identify critical deadlines, and to ensure efficient transfer of knowledge between team generations. What this includes is project infrastructure, organization, documentation, value analysis, planning, and monitoring. Good engineering practices also include like design reviews, the change in management and innovation, and the continuous improvement of every aspect throughout the process. And so this is what it means to have good engineering practice. So that is the end of my workshop. Thank you all for listening, and I hope you learned something here today, or at least relearned something, so that you can better understand the problem you're tackling, so that you're not caught up in a web of mess of trying to figure out what to do next. All right, I have one more session, but I hope to see you all there then, and hope you guys all have a great rest of your day or week.